Hello, geometry students. It's Mr. Zabo. We are finally back with some videos here, and we are going to cover two sections. Really, one of them is just this page here. Section 4.3 is a right angle theorem. It's something that we've seen. It's something that we've done. It says that if two angles are both supplementary and congruent, then they are both right angles. And we know this, and we've used it. Now we've got a formal definition and a formal theorem for it. And so our quick paragraph proof to describe this is if we are given that they're supplementary, or we can look at this and assume from the diagram they're supplementary, and told that they are congruent, then since they're congruent and they're supplementary, then they must be 180 degrees each, because that's the only way to make that happen. If they're 180 degrees total because they're supplementary, then each is 90 degrees. Since they're 90 degrees, they're right angles. It's as simple and straightforward as that, even if the wording in my paragraph proof might not be as simple or straightforward. The second section that we're going to move into is section 4.4. It's the equidistance theorem. This theorem is going to help us recognize relationships between the distance of points and perpendicular bisectors, or perpendicular bisection. So as we move into this section, we've got a few vocab terms, a couple of new ones, and then some review one real quick. When we talk about distance, we are always talking about a length of the shortest path between two segments or 2 points. Okay, the distance is always measured as the crow flies, is the way the saying goes. Okay, so the distance from your house to school, according to geometry, would be as the crow flies. If you could just float up and go directly there in a straight line, perfectly shortest path. We know that for the vast majority of us, that distance is longer because we have to take the roads. Okay, so we don't measure in geometry the distance with all these turns. Distance is measured in a straight line. A postulate for us then is a line segment is that shortest path between 2 points. Okay, so those two things go together when we're talking about distance. And then quick review of perpendicular bisector of a segment. It's a line that is both perpendicular to a segment and cuts it in half. Okay, so we've seen that, we've used that, we've studied that already. Moving into our newest theorem. If 2 points are the equidistant from the endpoints of a segment, so in this case, segment CD is our segment. If we said that point B is equidistant to C and D, and point A is also equidistant, that doesn't mean those two are the same distances from C and D, it means B is the same distance to C as it is to D, and A is the same distance to C as it is to D, then we say that they are determining, or they are on, the perpendicular bisector. Okay? So again, if we know B is the same distance to C and D, so BC is congruent to BD, and A is the same distance to C as it is to D, segment AC is congruent to segment AD, we can conclude that AB is a perpendicular bisector of CD. So the given is the equidistance there, the conclusion is the perpendicular bisector. When we're stating the perpendicular bisector, we want to make sure we state what is the bisector and what is being bisected. That's theorem 24. And then theorem 25 is very similar, but now it says if a point is on the perpendicular bisector, so now I would have to be given a perpendicular bisector. My conclusion is that it is equidistant from the endpoints of that segment. So if I am given that segment AB, or line AB, is the perpendicular bisector of segment CD, the diagram shows that because it's bisected and perpendicular, I can conclude that BC is congruent to BD. I can conclude that AC is congruent to AD because they are on the perpendicular bisector. Okay, AB is the perpendicular bisector, B is on the bisector, B is equidistant to points C and D, should say A is also on there. All right, let's take a look at this proof. Okay. We are given isosceles with legs A, B, and AC. D is the midpoint. We are trying to prove that AD is the perpendicular bisector. So we start with our given, including the fact that these are our legs. Okay, the legs being congruent is my next step. If it's isosceles, then that should have those marks in it, and it's hard to do that in PowerPoint. Then I'm given that D is the midpoint, so I know BD is congruent to DC. What I now know is that it's the perpendicular bisector. I have 2 points that are equidistant. 2 points determine a line, so that's good enough. D, being the midpoint, I know is equidistant to B and C. A, based on statement 2 here, because it's isosceles, is equidistant to B and C. If I have 2 points that are equidistant to endpoints, then I have a perpendicular bisector formed by the line connecting those 2 points. Okay, and our last proof is that given that it is the perpendicular bisector, prove that the triangles are congruent. Well, we know a number of things here. And its triangle PQS is congruent to triangle PRS. I know it's the perpendicular bisector, which means I know PQ is congruent to PR. Why? Because if it's a perpendicular bisector, we can just say it's equidistant. This point P is on the perpendicular bisector. It is equidistant to my endpoints. That is one congruent side. We know QS is congruent to SR for the same exact reason. S is on the perpendicular bisector. And we know that segment PS is congruent to itself by the reflexive property. Now by side, 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 my triangles are congruent. So this 2 proofs, we're trying to walk you through the 2 different ways you would use these theorems. Okay. We're going to have a couple of practice proofs here, and we're going to do some work with these in class as well.